Welcome everyone, all those who have joined. Am I audible? If yes, you can confirm in the chat box. Thank you. So let us take a few more minutes so that other audiences can join. Good morning and welcome everyone once again. Thank you for taking time to join today's webinar. My name is Piyashi Das and I'll be your host today for this webinar. Before we start, I would like to give you a small introduction about Yokogawa India Limited. Yokogawa Test and Measurement has been developing measurement solutions for over 100 years, consistently finding new ways to give R&D teams the tools needed to gain the best insights from their measurement strategies. Yokogawa Test and Measurement instruments are renowned for high levels of precision, accuracy, stability, and repeatability for the products and pioneers in the measurement of power, waveform, process, and optical parameters. Precise and effective measurement lies at the heart of successful innovation and has focused its own R&D on providing the tools that researchers and engineers need to address challenges. Our principals in Japan are in this field for over 100 plus years, and Yokogawa India has been in operation for 35 plus years in India. We have 6 regional offices and several branch offices spanning all over India. We also have a dedicated network of channel partners. Today in this webinar, our topic of discussion is Yokogawa Test and Calibration Solutions, presented by our product manager, Mr. Siddhalinga Swami, who has several years of rich experience in test and measurement division, and he is currently a product specialist working closely with Japan, TNM HQ. His visits to Japan and interaction on global solutions helps in taking care of process T&M instruments and basic instruments which are used across industries like power, process, automotive, oil and gas, food and pharma, etc. Few tips before we get started this webinar. So today's webinar is scheduled for 90 minutes. All participants will be muted to enable the speaker to present without any interruption. If you have any questions during this presentation, you may please type them into the QA box provided on the On24 control panel to the right of your screen. I'll bring them up after the presentation is complete, and we will also have time for questions at the end of the session. Finally, at the end of the session, you may leave your valuable feedback in the feedback form provided. So now it's the time to hand it over to our presenter, Mr. Siddhalinga Swami. You may please take over from here. Thank you.
Good morning to all the audience, and uh, thank you for the introduction, Ms. Piyashi. So we'll straight away move into the presentation now. So today's presentation is about Yokogawa Calibration Lab Solutions. So we are focusing on what are the products and solutions from Yokogawa with respect to calibration labs. So in this webinar, we are going to have an overview of what is calibration and what are the consequences if the instruments are not calibrated on time, and what are the types of duties we come across on daily basis in any of the industry or in any of the calibration lab, and what are the requirements for calibration lab and key factors to be considered for calibration of the test and measurement instruments. And finally, we'll throw some light on Yokogawa solutions for calibration labs. So from Yokogawa, what all we have with respect to meet the requirements of calibration labs. So what is calibration? So uh, basically calibration is to compare. So when these days when it comes to human beings, so there is a talk or there is a trend of saying that don't compare yourself with anybody, or do not compare, so everybody is individual. But when it comes to test and measurement instrument, it is not so. So any of the test and measurement instrument needs to be compared with the known standard or the master instrument which is of higher accuracy. So the process of comparison is called as calibration. In doing so, we check for the errors in the duties, and if at all any errors are there, we'll compare. We will correct those errors and we'll adjust the errors, and then we say it is calibrated for the defined specifications. So when we come across calibration, so there are set of procedures will be followed, such as operational procedure, measurement procedures, and calibration procedure and verification procedure. These are a couple of procedures which we come across during calibration. And when we do the calibration, we do two types of calibration: as found and as left. So as found is basically before correction or before adjusting the error, and as left is after correction. So we do two types of calibration. So usually calibration activity will be authenticated by a calibration curve and calibration report and calibration certificate provided by NABL accredited lab, and finally a traceability certificate. So these are all the reports or the set of documents which authenticate the calibration activity. Next, we'll discuss what are the consequences of not calibrating. So what will happen if the test and measurement instruments are not calibrated on time? So specifications are not guaranteed due to the natural drift or and behavior of the equipment. So that means when we do not calibrate our test and measurement instruments on time, so the defined specifications will not be guaranteed. So we may have to have a results which are out of specifications and which may not give the desired results. And out of calibration equipments leads to false testing and faulty manufacturing. Let us say, for example, an instrument which is there in which is lying in the production facility is not calibrated on time. So using that out of date calibrated or the non-calibrated instrument, if we do the testing of our products and if we proceed for manufacturing, we may end up having faulty products at the end of the day. Product recall is very expensive and complex. So once the products are manufactured with the non-calibrated instruments, so once it goes into the market, once the product recall or the getting back the manufactured products is very expensive. It is a cost. It adds cost to the company, and it is a entire complex process. We will get into the complex process of recalling the products. And lost reputation and brand value. Once the product is into the market with the out of specifications or the inferior specifications, so it will definitely and it will badly affect the reputation of the organization and brand value, and big financial implication and burden. So further it will lead to the loss of reputation, the loss of brand value further impact your business, and it may lead to the financial implications of the product and for the company, as well as it will be a burden on the company. And one of the most important thing is that doing the testing or doing the manufacturing with the out of date calibrated non calibrated instruments or out of date instruments. So in the first place, we are not complying to the process quality and metrology guidelines as per ISO 9001 2015 regulations, which is a compliance issue by itself. And loss of business opportunities. It will lead to the loss of business. You may lose the business opportunities because of inferior products, or the products which are of inferior specifications or wrong specifications. And loss of production, damage and safety compromise and fatality. If it is of a process industry, if you are considering a calibration of the instruments for a process industry, if it is having a erratic reading, if it is not calibrated on time, it may lead to a damage of the entire process plant, like a boiler blast or a burst of the pipeline if it is a process industry. So those kind of consequences also be faced. So then we'll move into what are the types of DUTs we come across. So DUTs basically, these are the instruments which are compared to the known standard or the master standards in the lab or in the field. Based upon different type of parameters, there are different type of DUTs which can be categorized. So for example, for physical parameters such as pressure, flow, level and temperature, those kind of parameters, we come across DUTs such as pressure transmitters and differential pressure transmitters, pressure switches, temperature gauges and temperature indicators. Those kind of DUTs will be there. For electrical parameters, when we say electrical parameters like AC/DC voltage, AC/DC current, power, frequency, power factor and resistance, capacitance, those are the electrical parameters. And pertaining to these parameters, will be having DUTs such as digital multimeters, clamp-on meters, power analyzers, power meters, energy meters and all. And coming to chemical parameters, we have defined parameters for liquids and gases. So when it comes to liquids, the parameters such as pH, turbidity, conductivity, these are certain parameters, and these will be analyzed or checked by using pH analyzers, conductivity analyzers, O2 analyzer, these kind of instruments. When it comes to gases, we have infrared parameters, we have ultraviolet parameters, chromatography, spectrometry, and the DUTs pertaining to these are thermal cameras and UV cameras. When it comes to mechanical parameters such as length, force, strain, torque, we will be having the DUTs such as tension meters, vibration sensors, sound meters, and strain gauges, those kind of instruments. So these are all the DUTs which we come across in any of the industry or any of the calibration lab in day-to-day activities. So next, what are the capabilities we have from Yokogawa with respect to calibration? So in this webinar, as we are focusing on electrical parameters and pressure parameter. So as you can see in the slide, these are the DUTs which will be able to calibrate from Yokogawa, which Yokogawa has the master products to calibrate all these DUTs. As you can see, multimeters and clamp-on meters, power meters, oscilloscopes, and panel meters such as panel indicators and analog voltage and current meters. These are the DUTs which we will be able to calibrate with respect to electrical parameters using Yokogawa standards. Then we have products such as pressure transmitters, temperature transmitters, and process indicators, which we will be able to calibrate using Yokogawa pressure standards. So in this webinar, we'll be focusing more on electrical parameters and pressure parameter. So next, what are the calibration requirements? What are the requirements of any of the calibration lab? So basic need is that any of the calibration lab should have reliable master instruments. So having a reliable master instruments in your lab is a prime most requirement. Means there should not be any compromise on having a reliable master instruments which can produce the results reliably, consistently over a period of time, and ease of operation of the master instruments. So master instrument should be in such a way that there should not be any much complexity involved with the operation, and it should be easily operatable, so that the much of the time can be saved with respect to calibration of the DUTs. And service and calibration support for the master instruments. So that means any of the master instruments available in the calibration lab should have a very minimum and very regulated service and calibration support, so that the downtime of the calibration can be reduced. So there should be easily available service and calibration support. So key factors to be considered for calibration labs. So in this webinar, we will discuss certain factors which are of prime importance when it comes to calibration. We will discuss on what is range, what is resolution, and what is uncertainty, and how test uncertainty ratio is defined, what is accuracy, what is test accuracy ratio, what is stability, and what is traceability. So in the further slides, we'll discuss in detail about these factors. So what is range? Range is basically what is the minimum value and the maximum value that can be measured by any of the measurement instruments. So that is called as range. So from the minimum value to the maximum value, it will be defined by a set of values defined in terms of minimum value and the maximum value. To be in a simpler way, it is a amount or extent, a parameter that can be measured by the instrument. And by doing so, there should not be any compromise on the defined accuracy. By complying to the accuracy, it has to measure the range of values. So for example, if it is for the electrical parameters, if you say voltage, current, so it will be defined in terms of 0 to 1000 volts, or 0 to 10, 0 to 100 degrees centigrade. And if it is for pressure, it will be defined like 0 to 10 bar, 100 bar, 1000 bar, like this. So when we say range, but however, when it comes to actual testing the input, the minimum value value of the input will be defined in terms of percentage of the full range. Like for the minimum input has to be whole range, or 1% of the defined range, like that. It will not exactly start from zero. Calibration. So it is a smallest change that can be identified by an instrument. For that, ideally, it will be the change in the least significant digit in the measured value. So ideally, it will be defined like 0.1 microvolts or 0.1 millivolts if it is for voltage. For current, it will be 0.001 microamps. If you look at the specifications of any of the product, so you will come across like resolution will be defined in these terms. Like if it's for resistance, it will be defined 0.001 ohm. So these are certain examples. So next is, what is uncertainty? So uncertainty is like any room for error, any room for change, or any room for to deviate is called as uncertainty. So, and it will be the uncertainty has to be measured for any of the test and measurement instrument. So it is a property of the measurement results that make them referable and comparable, and therefore corrected and regulated throughout the internal and external global market. So uncertainty is ideally defined in terms of percentage of full scale or percentage of reading. So uncertainty is like it is defined for a measurement T&M product. So where it will be checked for how much the deviation the results can go when any of the parameters is measured. So usually the uncertainty will be of combined standard uncertainties. It will be affected by a set of factors when we do the measurement, and those factors will be uncertainty due to environmental conditions such as temperature and humidity, and uncertainty due to skill of the operator, if at all any error is added because of the unskilled manpower, or uh, because of mistakes from the operator, that has an uncertainty also to be considered. And uncertainty because of measurement instrument. So by default the instrument will be having certain uncertainty because of voltage fluctuations or the semiconductors involved in the instrument, and uncertainty due to measurement method. So what kind of method and how, what method we are following for doing the testing, that also adds to the uncertainty. And incomplete sampling of the measurement, that means improper measurement of the parameter, that also adds to the uncertainty. So overall these factors will give us the combined uncertainty. So when we say uncertainty, it may affect our measurement and the test results in a very in a very in a very vast way, we can say, or in a very effective or way, we can say. That means we need to properly calculate and evaluate the uncertainties involved in the measurement. Then only we will be able to identify what what accuracy or what uncertainty master instrument should we have for the calibration. So that entire thing will be defined by proper evaluation of the measurement uncertainty or combined uncertainty. So usually uncertainty will be defined as or it will be measured like test uncertainty ratio. And test uncertainty ratio is a uncertainty of the DUT compared to the uncertainty of the standard what we are using. So reliability of the master instruments usually mentioned in terms of test uncertainty ratio, and TUR will be defined like a uncertainty of the DUT to the uncertainty of the standard what we are using. And what is measurement accuracy? So till now we discussed about the measurement uncertainty. So what is accuracy? What is the difference between uncertainty and accuracy? When we say accuracy, it is a qualitative indication of the ability of measurement instrument to give the responses close to the true value. So that means accuracy will be defined for controlled environment, such as from temperature of so and so degree to so and so degree, and humidity of so much percentage, and altitude of so much height. So accuracy will be defined for controlled environment. And accuracy will be basically it is a manufacturer specifications. And when we talk when we compare uncertainty to the accuracy, in uncertainty we are further considering the errors which will arise because of all other factors which we discussed in the previous slide. So reliability of the master instrument is also defined by test accuracy ratio. Test accuracy ratio is accuracy of the DUT compared to the accuracy of the standard which we are using. So further we will discuss how TUR and TR both are relevant in calibration labs, and how these are different, and how these ratios are used for these ratios are used to make decisions in the calibration labs. So TUR or TR are usually represented in terms of ratios as per ISO. TUR between DUT and master should be 1:4. So that means the ratio between uncertainty of the DUT to the uncertainty of the master should be 1:4. That means our master should be 4 times the accuracy of the uncertainty of the master should be 4 times better than that of the DUT. And TUR must meet the basic requirement of 1:4. Then only we can have a better test accuracy ratio. For example, let us consider a pressure gauge which is having 1% of accuracy, and we will calibrate this pressure gauge with the master gauge, which is having 0.2 percentage of accuracy. So here, if we see the ratio, we are meeting the basic requirement of 4 times better. Means the 1:4 ratio we are just crossing, and the TAR we have got as uh, full value of 5. That means the master gauge which we have chosen means to calibrate the pressure gauge which is having 1% error, and we are calibrating that gauge with the master gauge which is having 0.2%. That means the master gauge which we have chosen, it is meeting our requirement. So the master gauge which we have chosen is a right standard or right master instrument for calibration of the particular pressure gauge. Similarly, so next we will consider uh, how much, what kind of master gauge or the master calibrator we have to choose for the calibration of this 0.2 percentage of accuracy master gauge, which we seen in the previous example. So let us consider, if you are considering a master pressure calibrator having 0.06 percentage of accuracy. So we are calibrating this previous master gauge with this master pressure calibrator having 0.06 percentage. We are the test accuracy ratio achieved is 3.3. So that means this master pressure calibrator is not meeting the requirement of 1:4 ratio. So we need to consider a better pressure calibrator which is having a better accuracy. So we are considering the pressure calibrator which is having 0.04 percentage of accuracy. So here we are meeting the basic requirement of 1:4 ratio. So, and hence this pressure calibrator with 0.04 percentage of accuracy is acceptable, whereas 0.06 percentage of pressure calibrator is not acceptable. So we, in the previous slides, we saw about test accuracy ratio, and when it comes to test uncertainty ratio, TOR is also calculated in a similar manner. However, we need to consider we need to have an estimate of the measurement uncertainty, which will arise because of the various conditions such as lab environments and uncertainty raised because of manual error, and uncertainty because of the instrument itself. So these all factors will be considered. So we will take an example and we will see how test uncertainty ratio is calculated. If you see, for any of the DUT or any of the master, basic accuracy or basic error will be defined. So then there will be room for, and we need to consider the deviation or the error due to, for example, temperature change. So that error will be added, and error which may arise because of operator or because of manual intervention, we can say. So that accuracy also we need to consider, and then we will consider total error of the, or total uncertainty of the DUT and total uncertainty of the master. So ratio of these two will give us test uncertainty ratio. And here you can see, with all these factors considered, 0.25 percentage is the uncertainty of the DUT, and 0.0625 is the uncertainty of the master. And we are we are checking the ratio here, and the ratio we are getting is just, it is hitting the value 4. So it is equivalent to 4. So when test uncertainty ratio is 4, we are hitting the TAR value of 5. That means TAR is better than TUR. So master standard is acceptable as both TUR and TAR is meeting the criteria of equal to 4, greater than or equal to 4. That means our TAR cannot be lesser than our TUR. So that's what the information, or that's what we want to convey from the in these two slides. So we cannot have a lower TAR than TUR. And when it comes to decision making, TUR and TAR both are useful in measurement practice and can be used for acceptance and rejection decision making. So when it comes to a calibration lab or any of the process industry, to make decision whether the DUT is fit for installation in the field, or whether the DUT is fit for to be used for any of the application, that decision can be made by checking test uncertainty ratio as well as test accuracy ratio. Both are considered. And test uncertainty ratio is most useful in selecting calibration providers. So when we send any of the instrument for the calibration to any of the lab, so we can check what are their uncertainty, how are the uncertainties are checked in their calibration lab, and we can have a sample calibration certificate from them, and we can check, we can see how we can, to choose the better calibration providers, we can use test uncertainty ratio. Because ISO 17025, it mandates that all the calibration labs should document and evaluate the uncertainties existing in their labs. And test accuracy ratio is most useful in selecting the new measuring instrument. So whenever we go for purchasing, whenever you go for selecting the standard for our for our lab or for our industry or for our company, so we will check for the specifications from the manufacturer, and there we compare the test accuracy ratio. So it is most useful in selecting the new measuring instruments. And test uncertainty ratio and test accuracy ratio both are effective in selecting the master standards for lab. So when we go for a selection of the masters for lab or a master calibration instrument for lab, we need to check both test accuracy ratio as well as test uncertainty ratio. So next we will discuss on accuracies defined in percentage of full scale and percentage of reading. So when we come across any of the instrument, whether it can be DUT or it can be master, we always see the specifications for accuracy defined in percentage of full scale and percentage of reading. So with percentage of full scale, our error, the error value is going to remain constant across the range. We will be having a standard error or standard deviation across the defined range for that particular DUT. Whereas with percentage of reading, error will be calculated, or deviation will be defined for that particular value which is being displayed, or for that particular reading which is getting displayed. So we'll see what are the advantages of having a percentage of reading and what are the disadvantages of having a percentage of full scale. Both are effective, but we'll see how it makes difference to the measurement. For example, we'll consider a pressure transmitter of 100 bar range, which is having 0.01% of the full scale accuracy. If you see here, even if in the 100 bar range we are measuring the lower values such as 20 bar and 50 bar, our permissible error is going to remain constant. If you can see here, 0.01 will be the constant error across the range. Even if you are measuring 20 bar, the error is 0.01. Even if you are measuring 50 bar, the error is 0.01. And with the constant error, we will be having actual reading with the permissible error. So the range of the reading which we get with the permissible error will be more with respect to full scale accuracy. Whereas when it comes to reading accuracy, percentage of reading accuracy will give us the better result in comparison to percentage of full scale. We'll be able to have at least 2 times accurate readings with respect to this example. If you see, at 100 bar we will be having 0.01 error. At 50 bar we will be having 0.005 error. That means we are getting 2 times better results in lower ranges when we have a percentage of reading accuracy. So this is the table which explains us. At 100 bar range, we are having 0.01 percentage, 0.01 as the permissible error. When it comes to 50 bar, you can see our the range of reading with a permissible error, it has improved. So instead of from 49.99 with the percentage of full scale error, here we are having better value, which is further to the third decimal point. So in this graph, it is clearly shown how the percentage of reading and percentage of full scale is going to make difference to our values or the readings. As you can see, this red line indicates the constant error with the percentage of full scale, whereas this blue line indicates percentage of reading accuracy. Here you can see in the lower range, we are having a better or the lesser error, and we are having a better readings, whereas with the percentage of full scale it is constant across the range. And one more term which we come across when we talk about calibration is accuracy defined in parts per million. So what is parts per million? So any value or any measurement value which is divided by a million is called as parts per million. So usually it is also a alternative way of expressing an accuracy for test and measurement instruments, or for the source and the source standards. So we'll see an example. So let us say we are having a source which is able to source a nominal value of 120 volts. If you can see here how to define accuracy in terms of parts per million for this source. So when we define the accuracy in parts per million, so this 120 volts will be divided by 1 million, and we are getting a parts per million accuracy of 0.00012 volts. So when this ppm 1 ppm is multiplied by 10, 20, or let us say for example 100, so we are going to have what kind of accuracy it's going to give in terms of decimal points. So here, for example, if this parts per million is multiplied by 10, we are going to have 0.0012 volts error. If it is going to be 20 parts per million, we are going to have 0.0024 volts error. So further, so when we define a source of a 120 volts with 10 parts per million accuracy, so we are saying that 120 volts plus or minus 0.0012 volts, and the range of value what we get when we do the measurement, it will be from 119.9988 volts to 120.0012 volts. So this is an example of how parts per million accuracy is calculated. So next two terms what we come across in calibration labs is the stability and traceability. So what is stability? So stability is how and to what extent can instrument will be able to retain its value without changing, and with meeting the accuracy defined for a specified period of time. So for any measurement, it should hold or it should retain its value for a period of time. Then only we'll be able to have then only we can say we have a better master instrument or better standard, and in doing so we'll be able to do effective calibration. Then comes the traceability. Traceability is basically a chain link between from DUTs to the primary standard, then to the standards which are defined in premier institute or the standard labs such as NMIS and NPL, those kind of institutes. So basically it is a calibration chain, means we are having a link between from DUT, the calibration of the DUT to the calibration of the master standards. Then they further the chain will further goes up to the primary standards, then to the NPL or NMI, National Meteorology Institute, those kind of institutes. So usually traceability chart will be indicated by a pyramid, where at the lower end we'll be having DUTs, and we'll be calibrating DUTs with the working standards. There will be a traceability certificate between these two, and further working standards will be further calibrated with the master instruments in the secondary standards, which are further traced to the primary standards, and these primary standards will be having traceability to the National Meteorology Institutes and NIC standard, those kind of institutes. Now we enter into the slide which is of more focus, we can say. So from Yokogawa, what products and solutions we have for calibration labs. So from Yokogawa, we have got range of products for electrical calibration applications like AC/DC voltage and AC/DC current, power calibration, those kind of parameters. Below are the products. So we have got master instruments with respect to voltage and current, and for power calibration we have got digital multimeters, digital manometers, and pressure calibrators for process applications. We have got multifunction calibrators. We have got oscilloscopes and data logger calibration capability, and we have got source and measurement units, and we have got function generators. In the next slides we will focus on couple of standard instruments which we have, and we'll discuss in detail. So we have got voltage and current standards for AC parameters. So we got high accurate voltage and current calibrators with the best resolution available in the market, and these are the standalone solutions for calibration of our panel meters, clamp-on meters, CTs, those kind of products. So this is how the product looks like, and the model number is 25588. It is a precision AC calibrator. It has got voltage range from as minimum as 1 millivolts to 1200 volts. So when it comes to voltage, yeah, we are having a decent range starting from 1.00 millivolts to 1200 volts. But what about current range? If you see the current range here, it is from 1.00 milliamps to 60 amps. So with this standalone product, you will be able to calibrate current devices starting from 1 milliamps to 60 amps. So this is a very wide range, covering a wide range of applications. So this is one of the unique feature of this product, which is a wide current range. It has got frequency also. If you see here, it covers applications ranging from 40 hertz to 1000 hertz. So when it comes to current and frequency, this product has got a very wide range, covering very major applications as well as very critical applications with a very minimum milliamps range kind of applications. What is accuracy? So in previous slide we saw how the accuracy is defined in terms of parts per million. So anything divided by a million will be a parts per million. Here you can see the accuracy defined in terms of parts per million. For AC voltage it is 400 parts per million, and for AC current it is 650 parts per million. So accuracy is also very high accuracy, we can say, with respect to AC current and AC voltage parameter. And it has got 5-digit LED display. As you can see in the image, it has got LED display with various knobs to change the ranges. And it has got built-in sweep functions. So you can see the various knobs and various switches which are visible here. We'll be able to create source patterns using sweep functions. Means we can define the steps, we can define the time interval, and it will source the values defined for particular time period. It has got output divider function. So that means we'll be able to source the value in terms of ratios like 1/4, 3/4, 1/15, 1/10, 2/10. Those kind of ratios we'll be able to source the value in terms of ratios which are critical for checking of the very critical applications such as uh, uh, current meters, current clamp, those kind of CTs where accuracy will be defined for each step. So for those kind of applications, this output divider function will be useful. And direct readout of the deviation will be able to view the delta. The deviation will be defined by delta in calibration labs. So that will be able to directly show here in the product. And it has got USB, Ethernet, and GPIB communication interface, which will be useful for if you are having a calibration software in your lab, which every lab does. So remotely we will be able to operate these products, and we will be able to control these instruments remotely with the help of USB and Ethernet, and we will be able to fetch the data through these communication interface features. Next, we have got voltage and current standard for DC applications. So you can see here in this we have got two models, 2560A and 2553A. These are also high accurate voltage and current calibrators, best available in the market with the best possible resolution. And these are suitable for calibration and testing of the analog meters, temperature controllers, sensors, and sensor transformers, multimeters, those kind of applications. So we'll focus on each individual 2560A and 2553A in detail. So here also, if we can see, voltage range is up to 1000 volts, which is again a wide range, we can say. Current range up to 30 amps. So it will be, with this calibrator, we will be able to cover voltage up to 1000 volts and current up to 30 amps. And it has got a capability to source temperature parameters also, like RTDs and thermocouples, resistance up to 400 ohms. And finally comes to the accuracy. So if you see here, the DC voltage accuracy is 50 parts per million and DC current accuracy is 70 parts per million. So in this range, with this product, this is the best accuracy available uh, with the economic model, we can say. If you want to go further, these are the best accuracy available. And it has got a resolution of 5.5 digit as well as 6.5 digit 6.5 digit display resolution. And then we have model called as 2553A. This is also a precision DC calibrator, which has got voltage range up to 30 volts and current range up to 100 milliamps. This also covers temperature and RTD up to temperature and resistance up to 400 ohms. And accuracy is, if you can see the accuracy, it is 75 parts per million for DC voltage and 120 parts per million for DC current. This has also got a 5.5 digit display resolution. If you see both 2560 and 2553A, 2553A is it's a must-have product for if you are looking for something in lower voltage and lower current applications, such as process calibration of the process indicators, process panel parameters, panel meters which are installed in the process industry, those kind of DUTs. Whereas 2560A, it is a must-have product if you are working on a higher range of DC current and DC voltage applications, since it has got a wide range of voltage range as well as current range up to 30 amps. Next we have AC power calibrator model called as LS3300. So as you can see here, it is a calibrator which covers both voltage, current. Along with that, it has got a capability to do the power calibration with the best possible resolution. So this is most suitable master standard for calibration of the power analyzers, power quality analyzers, energy meters, power transducers, those kind of DUTs. And the people who are into the manufacturing of industrial equipment, such as voltage indicators, current indicators, and energy meters for panel, or low range power quality analyzers, energy loggers, those kind of instruments, this product is must have for those kind of customers. And if you can see here, the voltage range is from 0 volts to 1250 volts. So I think this is the decent AC power calibrator with such a wide range of voltage, starting from 0 volts to 1250 volts. When it comes to current range also, if you can see here, from 0 milliamps to 62.5 amps. So what we are indicating with these ranges is that this calibrator has got the capability to do the calibration and calibration of voltage and current range, along with the power, covering this entire range. So your entire power calibration can be voltage and current range. Frequency from 40 to 1200 hertz, and accuracy also, if you can see here, it is 350 parts per million for AC voltage and 450 parts per million for AC current. And it has got a AC power accuracy up to 450 parts per million. AC power accuracy is also on very high side, and it has got the capability to calibrate power factor as well as phase angle also. And as we discussed in the previous slides for the AC and DC master standards, this has also got built-in sweep functions where we'll be able to create source patterns. And it has also got USB and Ethernet communication for serial interface and remotely operating this master instrument, as well as this, as we discussed, this is suitable for calibration of the power meters, power quality analyzers, and those kind of instruments. Next, we have got a 6.5 digit benchtop digital multimeter. The model number is DM7560. In this, we have voltage range from DC 1000 volts and AC 750 volts, and it has got current range from 0 milliamps to 3 milliamps, and frequency covering 3 hertz to 300 kilohertz. It has got accuracy of 0.0035% of for voltage and 0.05% of the reading for DC current. It has also got capability to measure RTD for in 2 wire, 3 wire, 4 wire combination, as well as it can also take thermocouple input. And it has also got a scaling feature. That means we'll be able to measure higher values of voltage and current through CTs and PTs. And a couple of applications where this benchtop DMM can be used is that monitoring of the battery current. As you can see here, the current range for this 6.5 digit multimeter is up to 3 milliamps. So monitoring of the battery current, which for monitoring of the battery current, that means to measure the very minimum current, this can be used. And R&D labs where checking and testing of the very minimum current in the lower ranges is very much crucial. There it can be used. Sensor testing, it can be used, and voltage reference testing. That means if you are designing a voltage source, so voltage source will be having a voltage references which generate voltages inside the unit. So it is very critical to check how effective or how accurate is the voltage references which are designed for those kind of sources. So those kind of voltage reference testing can be done using this multimeter, and this can be a product for your calibration bench also. So next we will have a discussion with respect to pressure calibration capability. So we have got the MT digital manometers model called as MT300. So these are the manometers with high accuracy and long-term stability, and these are designed with the Yokogawa's patented sensor technology called a silicon resonance sensor. So I'll just throw some light on what is the silicon resonance sensor. Silicon resonance sensor, basically it is a sensor technology developed by Yokogawa, where it is a digital sensor which gives directly frequency output, unlike our piezoelectric sensor where piezo resistance and piezo capacitance is involved. Over a period of time, they are bound to drift, and they are bound to develop errors due to electrical parameters, and because of A to D conversion, they are bound to drift. Whereas this silicon resonance sensor, we call it as a drift-free sensor. It will easily run for 5 to 10 years without any drift. Since it is giving a direct frequency output, there is no room for A to D conversion error, and there is no room for errors developed because of electrical parameters. So from that point of view, it is the most stable sensing technology available in the market. So these manometers will be having this silicon resonance sensor as a pressure sensing element in the inside. In this, we have got a gauge type, differential type, and absolute type. In gauge type, we have got 6 ranges starting from 10 kilopascal to 70 megapascal. In absolute ranges, we have got 130 kPa to 3500 kPa. 3 ranges we have. We also have got differential pressure manometer to cover the calibration of differential pressure differential pressure transmitter and the devices which work on differential pressure. So we have got 4 ranges starting from 1 kPa to 700 kPa. So one of the importance of these manometers is with respect to accuracy and resolution. As you can see here, these manometers have 0.02% of the reading. In the previous slide, we discussed what is full scale error, what is percentage of reading error, and how it is going to define the accuracy of the particular or the capability of the particular master instrument. So from that perspective, these manometers have got 0.02% of the reading accuracy, which is highest available in these ranges, and resolution of 0.0001 kPa. Resolution is also, we will be able to measure the pressure deviation up to the 4th decimal point. So it is one of the best possible resolution available. So from application perspective, we have got these instruments can be used for calibration of the transmitters, pressure gauges, pressure switches, and testing and calibration of the ventilators. This is one of the prime applications which we are discussing now. So testing and calibration of the ventilators. When we talk about ventilators, ventilators will be dealing with a very minimum pressure. So these are involved. These are ventilators are for checking of the air pressure of the lungs or the air pressure of the human respiration. Very minimum pressure will be involved. So it is very critical and important to measure the pressure or the available pressure there and how effectively those pressures are measured. So for those kind of application, these products are very useful. And when it comes to calibration lab, since these have got a display with the best, highest resolution and highest accuracy, so these can be part of your pressure balance as a indicators also. And this can be used for evaluation of fuel pressure sensors in automotive industry. Then we have got a model called as CA700, and this is suitable for field calibration activity. And as we discussed, this also has a silicon resonance sensor as a pressure sensing element. One of the main feature of this product is that this has got the capability to generate the report, and we can set the tolerance percentage in the calibrator. With that, you will be able to it will be able to generate pass fail report can be generated, whether the done calibration is okay for particular step or not, that can be decided. In this, we have got a range from minus 0.9 bar in the vacuum to 35 bar in the positive pressure with an inbuilt sensor. It can be extended up to 700 bar with the external pressure module called as PM100. And it has also got source and measurement capability for milliamps and voltage, and it has also got a capability for loop power feature. Accuracy is 0.01% of the reading, and resolution is also very high, 0.001 kPa. This is more suitable for calibration of the pressure transmitters, pressure gauges in the field, as well as for loop checking of the transmitters and evaluation of the pressure sensors in the automotive industry, those kind of applications. Then we have got a multifunction calibrator models called as CA500 and CA550. These calibrators will cover your basic process requirements, such as covering process source and measurement parameters such as voltage, milliamps, thermocouples, RTD, frequency, pulse, those kind of parameters. And it has also got loop power capability, and it has also got built-in sweep functions to create various source patterns as per application requirement. It covers all 17 type of thermocouples and 14 type of RTDs with the accuracy of 0.015% of the setting for the source section, and 0.015% of the reading for measurement section. In this, we have got one more model called as CA550. It is a simple hard communication feature is added for this particular calibrator, where we will be able to do some basic hard communication functions in the field, such as reading of the tag number and checking the primary value, secondary value, those kind of things. And we will be able to read and write both lower range value and upper range value, and we will be able to change the damping constant. And we'll also be able to do the trimming of the 4 milliamps, trimming of the 20 milliamps, and zero trimming also possible using this CA550. This is most suitable calibrator for field applications and field hard applications, as we'll be carrying out these activities in day in and day out in any of the process industry. So next we'll discuss what are the application areas of Yokogawa products and solutions. So when we talk about application areas from Yokogawa, we have got our in-house calibration capability also. We have got our own in-house calibration lab, where we will be able to calibrate all the instruments such as power meters, energy meters, multimeters, oscilloscopes, and those kind of instruments. So, and we are using our own master standards in our lab, which are of very helpful in uh, calibrating test and measurement instruments of different makes and different models. So in this slide, we'll focus on application areas of Yokogawa products and solutions. So with this product, this is one of the key focus slide we can say. So with our products, we'll be able to help to set up in-house calibration labs for process industries. So we'll be able to give you a complete solution with the Yokogawa standards. If you are planning to set up a lab for your in your process industry. Let us say, for example, there is a process industry who want to start their in-house calibration, start doing the calibration in their own facility. So these are the products to start with. These are the master instrument to start with, we can say. And enhancement and upgradation of the existing cal lab facilities. So if you are looking for enhancing or the upgradation of your existing calibration lab facilities, so these are the products you should go for. And creating and duplicating cal lab setup at a lower cost for higher productivity. Let us say, for example, if you are having a already calibration lab which is covering a range of electrical parameters, so but the workload on your existing master standard is more. If you want to have a parallel bandwidth created for the calibration. Let us say, for example, if you are having a high accurate voltage and current standard, and your entire workload is on that particular master standard, so you'll be able to make a bifurcation that if you you'll be able to make a bifurcation that lower standard or lower accurate instruments has to be taken away from that standard, and you can have a parallel bandwidth created with these Yokogawa products for setting up of a parallel capability, we can say. And these are the instruments which are useful in to have in calibration and repair benches. So if you are a T&M manufacturer, so if you are manufacturing the instruments such as energy meters or panel meters, panel indicators, voltage meters or current meters or clamp on meters, those kind of products, so these are the must have products for your testing requirements, for your electrical testing requirements for your product. So you can do the first hand checking or production quality testing or in-house lab testing you can do for your products. And if you are looking for a new calibration lab setup, we'll be able to do with these products starting from the consultation to the full-fledged installation. So with these products we'll be able to help you. Finally, we can do system calibration and verification. So if you are already having a system like a test bench or a calibration bench, so you want to further calibrate that system or further verify that system whether it is working to the expected level or not, that entire solution can be given. That entire solution capability we have from our Yokogawa standard products, and we will be able to help you with the system calibration or system verification. So this comes to the end of the session. So our aim is to enhance your calibration with Yokogawa products. So our focus is you can enhance your existing calibration lab with Yokogawa standard products and Yokogawa solutions. Thank you. So for any inquiries, you can always write to us on the mentioned email ID, and you can always contact us.
We are the precision makers.